Good evening, everyone. It is currently 8:30, and we are here with Chapter 2. So, Chapter 2 covers objects and classes, but I wanted to spend some time working with pointers because we, let's face it, we're going to be working with a lot of pointers in this class. So, if you know them, if you know them well, the better off you'll be. So, one way that I like to think about pointers, and I'm probably wrong in thinking about this, is a pointer is a data type augment. So on the left here, we have a integer called num, and it's set equal to 4 right now. On the right, we have a integer pointer named pointer, and we are setting it equal to ampersand num. Before I delve into what a pointer is and all of that fun stuff, I want you to understand what happens in memory whenever you work in it. So down here, we have a couple numbers. We have OX0, just an arbitrary memory address, and the value part of it. So memory can be thought of kind of like a coin. On one side, you have memory, and on the other side, you have the value that is stored in that memory. So, for example, we have num equal to 4, so that says make a spot in memory big enough for an integer. I believe integers are, we're going to say 2 bytes. So give me 2 bytes of memory and put the number 4 in it. So if we come down to our makeshift memory down here, we have OX0 has the value 4. So whenever we start working with pointers, the pointers are going to mainly focus on the memory side of things, whereas just normal variables focus on the value side of things. So looking at this monstrosity of a line, we're going to break it down a little bit. So scroll down and rewrite it. We have int star pointer is equal to ampersand num. So looking at it, it's ugly. Let's just be honest. So going piece by piece with this, we are saying, okay, I need 2 bytes of memory for my integer, but I want to focus on the memory. Named it pointer like any good variable, and now we have ampersand num. What this says is take our number, and instead of pulling the value at it, if we didn't have this ampersand, it would be 4. I want to grab the memory of it. So this is saying create a int pointer and set it equal to OX0. If we used a different data type, so let's say our number was actually a float, so let me do float, help if I could spell, x is equal to 8.0. So we know that a float, if we Google it right now, is going to be 4 bytes. And we try to use a int pointer, which only sets aside space for 2 bytes. So as much as I would love to draw out all 32 bits of this, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 6, you get the idea. So the float has 32 bits of memory that it can work with. If we only use an integer, we are going to lose half of those bits. While it may not matter for smaller numbers like 8, for bigger numbers, we are losing all of this. So literally half of the number. So, random rant, I know, but so integers and pointers, going back to it, pointers and numbers. So we have number equals 4, and we have our pointer pointing to, who would have guessed, num, ampersand num. If we just want to outright get the memory from our number, we have to add the ampersand to it. So if you open your terminal, open VS Code, whatever you're typing in, and you type cout num, you're going to get the number 4. Crazy. If you were to type cout ampersand num, you're going to get the memory address of num. So that's going to be 0x0, as we had it up there. It's arbitrary, it doesn't matter. So pointers work in the opposite direction. So if we take our pointer that we set to num, and we cout pointer, we are going to get the memory address of pointer, so 0x0. If we want to get the value out of pointer, we have to add a star to pointer and dereference it. So star pointer. This will output 4. So the reason I drew this chart up here of the memory and the value is it's the flip side. So with our number, if we normally work with it, we get the value side of it. Do I have something I can flip? I'll do my phone. So let's say camera side is value side. By saying cout num, we get the number, but what if we want the memory of it? We add the ampersand, and we get the other side. Pointer is the opposite way. If we just say pointer, we get the memory. If we get the flip side, we get the value. So somewhere in these 15 tabs I have open, there it is, I built sort of a example program for you to look at. Make sure I'm not showing any answers by accident. So once again, we have the boilerplate for C++. We have #include IOStream, so we can use C and cout. Using namespace standard, it's not good programming practice to input that. If you really wanted to, you could just import endline C and... No. I'm lying. So the C and cout are from the C standard library. So without this, you would have to type standard cin or standard cout. I'm lazy, so if you get a big person job, don't use this unless you're told you can. So we have 2 functions. I threw them in functions. You could also get a refresher on functions. We have num and pointer and array. So I'm going to go ahead and comment out num and pointer. And this is just a code example of what we just talked about. So we set num equal to 4, and we set pointer equal to num. We print it normally, so num is equal to 4, and pointer is equal to whatever memory address it may be. And then if we take the memory address of num by putting ampersand num, we get the memory address. And if we dereference our pointer, we will get 4. So let me go ahead and run that for you. You can see I already ran it once. So compile it with G++ and whatever your file is. So num is equal to 4. Pointer is equal to 0x7FFE13CDD7AC. The dereferenced number is equal to the exact same memory address. And the dereferenced pointer is equal to 4. So, flip side of the coin. Next thing I do want to run my mouth about. Ooh, I forgot to erase that. 1 second. Close enough. Is working with pointers and arrays. So, on the screen already, I have my array. It has 4 elements, 0, 1, 2, and 3. And we have a pointer pointing to that array. So, put that back. I don't want to see that. Whenever we normally work with arrays, we have to index into them. So, if we say my array at 0, the number that comes out is going to be 0. Shocking. If we want to get, array at 1, we are going to get 1 out. Array of 2 gives us 2. I do want to take a detour and discuss how numbers are stored, arrays are stored in memory. So if you want to, if you get really bored following along, you can open up some sort of terminal, some sort of program, and just go ahead and print my array. What you'll find is it just gives you a memory address. So let's just say OXF. And, add letters to your heart's content. Ooh, more erasing. Ooh, you didn't see any of this. I wasn't practicing. So if we print OXF, if we were to dereference the first value of our array, we would get that same memory address. Because whenever arrays are stored in memory, so this first value, whenever we print my array, is actually the address of the first element. So making our makeshift memory value chart, so mem val, what actually gets stored in memory is at OXF, we are going to have 0. At OXF2, because we're assuming that an integer is 2 bytes, we are going to have 1. At OXF4, we're going to have 2. And at OXF6, we're going to have 3. So there's a little deep dive on how your arrays actually work. So we know that we can access arrays using array notation, but there also exists pointer notation. So we're going to take this magical pointer that we made, int star, so we want a pointer to an integer, and we're pointing it to the first index of my array. So coming down here, what we can do is we can cout pointer, and this is going to give us the OXF once again, because we assign the memory address of the array to pointer. What if we want values out of this pointer? What we can do instead is throw on a star, parentheses, pointer, parentheses. What this says is go to pointer and get me whatever value is at this address, which in this case would be 0. I'll label this output. So the other thing that happens with pointers is what if we want not just the head of the array, but we want the next value? What we would do then is output star pointer plus 1. So if you'll remember, we have integers, right? So what this boils down to is saying, hey, go to OXF and then add 2 bytes. So 2 bytes times whatever spot you want to be at. So let's say n, which in this case n is 1. So it's saying, hey, go to OXF2 and get me that value. Well, we already know that value, which is 1. So the thing with arrays and pointers is that they can be essentially mixed and matched. You could use pointer notation. So pointer, this will give us 0. You could say pointer at index 0, and this will give us 0. You could say my array. Let's say we want the second index, or third index, I guess. My bad. This is going to give us 2. You could also say my array. I'm blanking. At the second index is equal to 2. So you can really mix and match these depending on what you need. So if we comment out num and pointer and look at pointer and array, I have the exact same thing built. So we have a integer array of 0, 1, 2, and 3. We have a pointer pointing to the array. And all we're doing is, let me swap these two. We're saying, okay, was the memory address of the first element of this array? What is the memory address of our pointer? So these two will be the same. We're saying what are the values of array at 0. And then this is the exact same thing. I'm actually going to add 2 to this. So now we can get the values of array at 2. So we have array notation and pointer notation. So go back to our terminal, g++ test.cpp, run it. So array, that's the memory. We have the pointer, which it's pointing to the exact same spot. I'd hope it's the same. We have array notation, so a of 0 and pointer of 0. They're the same. Then we have pointer notation, so array plus 2 with a star. And the values are correct. Crazy. So, where is it? There we go. So, you only want to use, I won't say only, there are hundreds of reasons to use pointers. But you have to keep in mind that you have to add a star whenever you're working with a pointer. So if I had a array of integer pointers, not sure why, but let's go with it. So int pointer, I'm so sorry I'm writing sideways. So fill this with random values. Whenever we come down here and we want to point to our array, we're going to have to use a int star star, my pointer. So whenever you want to point to something, add a star. So that's your crash course on pointers. I hope you learned something. So now on to Chapter 2, Objects and Classes. Once again, this is more or less just review, but maybe you'll learn something. So to start, we have classes and objects. So classes and structs are extremely similar. If you look on Google, everyone on Stack Overflow will call you an idiot and tell you that it's the exact same thing, minus a very small detail. So in this class, we're going to try to separate the two. Classes are fantastic for object-oriented programming. We'll touch on that a little bit later, but all you need to know for now is that it's when we want to work with something that's more in-depth than just variables. Structs are fantastic for just making our own variables. They are chef's kiss. So classes and structs are similar because they allow bundles of related variables. If I wanted to make, let's say a store. Well, each one of my products, they're going to need a price. It's going to need some sort of barcode identifier, and usually some sort of, not identifier, but a descriptor. So maybe put the fruits together, put the veggies together. All of those can be bundled. The syntax of a class declaration is quite similar to the syntax of a structure declaration. This third point, I had to kind of wrap my head around. So whenever we work with structs, we make variables. And, whenever we work with classes, it's technically objects. So objects are they're variables, but more to it than just that. So an object is a instance of a class, so one single instance, in the same way that a variable is an instance of a structure. So if you have to chew on that, go ahead and pause, take a couple of seconds, and we can scoot on. So a class is quite literally just a blueprint. And these objects that we talk about are houses we build from the blueprint. If you look around Cookville at any, two-story apartment, it's the exact same layout. Give or take, kitchen being in the front or back. But regardless, this apartment class that we have is creating multiple objects, multiple similar objects. So classes can be broken down into a couple different pieces. The most important ones are attributes and member functions. The attributes of a class are the data members. It's the variables of a class. The member functions are the functions that belong to that class. One thing that I always brought up with my class last semester is that member functions are... I'll leave it for the next slide. It's next slide, yeah. So you'll hear the term encapsulation quite a bit. And what that is just combining data and member functions into an object and hiding what the user doesn't want to see. It's similar to abstraction, in which we are trying to make it a simple process for the user, whether it be, how do I drive a car? How do I play this video game? And whatnot. So within classes, one thing that you'll obviously want to do is hide your data. Abstraction, whatnot. It restricts the access to certain members of an object. So, the example I used to always tell my class was, if I came up and asked for your social security number, I would hope you wouldn't give it to me. You should be hiding that data. Because in this example, I am outside code. I should not be allowed access to your social security number, one of your attributes. There should not be a member function for me to get that. But if I was outside code and I was working with a member function to get, let's say, your name, that seems pretty innocent. So another great thing to look at with classes and object-oriented programming is reusability. There is a programming saying, paradigm, whatever you want to call it, called dry. So I'm going to go ahead and dry. Why is it? It's red now. Let's go with that. So dry. It stands for don't repeat yourself. What it mostly means is if you are having to create these objects multiple times, why are you doing that? And you are wasting time. So real world program is never written by one person. Every C++ program has used objects. So cin, cout, and string objects are all examples. Object-oriented programming is great because we can reuse the code easily. It's easier to hand someone, an instruction manual on how to build a car than to just throw every piece and part at them and say, good luck. So within our objects, we want our users to have a object interface. What do I need to work with this object? A great thing is a car. If you hand me a car but don't teach me how to use it, it's going to be a very nice shelf. So I need to know how to work the interface, the steering wheel, the gear shift, gas pedal, brake, ignition, and mirrors. The object interface should be separate from its implementation. The user of an object only needs to know the interface. If you think to Apple, I know how to work an Apple phone. Can I repair it? Probably not. Not with my current skill set. So, now the fun part, we get to look at code. Yes! So, on the screen, we have a very simple class example just called book. It has 3 attributes. It has number of pages. It has a string, which is its title. And it has a float price. It has two member functions, a setNumPages and a getNumPages. So whenever we want to work with this class, we have to make an instance of our object. So code on screen, we have int main, we're going to create my favorite book with the data type book. Then we take our favorite book and we set the number of pages equal to, let's say, 156. To access this, we use the dot operator. If you're working with pointers, you want to use the arrow operator, the like minus sign, alligator sign. So with classes, we talked about data hiding, and this is the slide for it. We have two different accessors in classes. We have a private and public access. Private basically says, hey, only my book object should be able to access these and change these. We have the public access specifier that says, hey, this is how you interface with num pages, title, price, usually through setters and getters. So defining functions for our class can be done in two different ways. I don't know where that other slide is, but this is the default function. So we have data type void. We say, hey, for the book class, : I want to define setNumPages. The scope resolution operator just says, hey, go look at this class. This is where this definition is. For our getNumPages, we can tack a constant on there, or a const, just saying, hey, compiler, we will not be messing with this variable, I promise. Because it's a getter, we only get the variable from it. So with this example, we have oop.cpp. That's a little blown up. So if we look through, we have our class book. With our private accessor, we have an ID, a book name, and an author name. Within our public accessor, we have set book name, set author name, get author name, and get book name. So you can define your functions in two different ways, either by doing the book : or you can define it directly in the class. So whichever one floats your boat. Down in our main, we have a book, and we are making an instance of a book, naming it B. We are using .setBookName, the giver. So we're saying, hey, use this function, setBookName, and set the private variable bookname equal to this. And if we don't use this, like this commented outline right here, it will complain. It will throw an error and say, hey, that's a private variable, you can't touch that. To print this, we do b.getBookName, and we see out what it returns. This makes a call to the define member functions by using the object b. So if we go and run it, and it is not there, my bad. There it is. So compiling it, we're going to do g++ oop.cpp and then run it. That's ugly, but we get the output, the giver, from this line 50 cout b.getBookName. So here's some practice for you if you really want it. Create a class named Planet. Planet should have 3 attributes: minimum surface temperature, maximum surface temperature, and size. So make sure your attributes are hidden from the outside code and use setters and getters to access them. Moving on to member functions. So we have mutator functions to start. A mutator function is also called a setter. can be interchanged. You will almost always hear me call it a setter. I have 5 brain cells, and 4 of them are remembering setters. We have an example of a mutator function below. So we have our function called set num pages. I'm losing it. We have a book set num pages, and it takes a integer named num. Then in the actual code, we just set num pages equal to num. This is saying, hey, from this book that we called this from, take the num pages and change it. Next, we have an accessor function. So an accessor function is a function that gets or accesses member data but doesn't change it. Once again, I'll almost always call it a getter. Below is an example of an accessor function. So whenever we call it from our object B, it's going to look at B and say, hey, grab B's num pages and return it. The const at the end, it's optional. I never wrote it in. Don't tell anyone. So for an example of accessor and mutator, we have rectangle version 1, and I guessed correctly for once. So looking at rectangle.h first, we have a rectangle class which has a width and a length for its private members, and then for its setters and getters, we have set width, set length, get width, get length, and get area. So looking at the implementation of these, for set width, it takes a double as a parameter. If w is greater than 0, we update the class's width, and if it's not, we quit. Length is the exact same way. Check if it's greater than 0. If it's not, quit. And then we have our getters or our accessors. So all it's doing is saying, hey, go to our rectangle object and return the width, return the length, and then finally we have an extra one called get area. What this is doing is it's taking the width and the length from our rectangle object, multiplying them together, and then returning the value. So looking at this function, we have a rectangle named box, and we have 2 variables that we are inputting these numbers into. This program will calculate the area of a rectangle. What is the width? User inputs the width. What is the length? User inputs the length. We update these variables within our rectangle, and then we print them out. So do I have this? Yes, I do. So g++ all.cpp, then we're going to run the file. This program will calculate the area of a rectangle. What is the width? 14, and for the length we're saying 10. So width is 14, length is 10, and area is 140. If we run this again and we say 0, well, it's less than or equal to 0. So let's try -1, -1, invalid width. So there's food for thought. So inline member functions, it is functions that is declared in the class declaration. I'm going to skip this one because I did show it off in oop.cpp, where we are just putting the function in public, our setters or getters. Another class practice, hope you're still bored. Add 6 inline member functions within the planet class, a setter and getter or a mutator and accessor for each attribute. It's going to be a whole lot of copy pasting, get variable, set variable. Create a source code file named myplanet.cpp and test your new class by creating an instance and calling some of the member functions, so just make sure it works. Now take the 6 you just created and place the function definitions in a separate source file called planet.cpp. So you did all that work inside your function, now move it. Good luck. So, private member functions. These are functions that aren't under public, they're under private instead. They're called helper functions. They're mostly used just to process data by the class and to get, following the dry principle, don't repeat yourself, just so you don't have to keep doing that for your class. It's internal processing, not for use outside of the class. So these are quality of life functions, really. Constructors, destructors, stuff like that. So constructors are automatically called when an object is created. So whenever you say, rectangle R, constructor is called. Even if you don't write a constructor for it, your constructor is still called. So for the default constructor, we have rectangle. It's the class name. So in this case, rectangle, 2 parentheses, open and close parentheses, semicolon. That is all the prototype is. So defining our constructor function, we can say rectangle, : rectangle. So with our rectangle class, we are defining the rectangle constructor. And in this constructor, we are just setting width and length equal to 0. So example of default constructor, rectangle version 3. Open. Okay, so where to start? That is version 2. Don't save. I have too much stuff open. So within our driver, we create a rectangle box, and then we just print the rectangle's data. So the difference with this is we have a constructor. And looking at the constructor definition, it's going to say 8.0 for our width and 9.5 for our length. And then when this object is created, it's going to say, hey, I'm in the constructor. Let's go. So that will print before all of this. And then we're just outputting what happens with it. So rectangle version 3. We create our G++ all.cpp. Oop. There we go. So I'm in the constructor, yay! So that gets called whenever we make our object. Here's the rectangle's data. Width is equal to 8, length is equal to 9.5, area is 76. So 8.0, 9.5, they are both doubles. It works. Crazy. Gonna clean this up a little bit. So next on it is overloaded constructors. It is the exact same as a constructor, but it takes arguments. If you'll recall from 1300, a overloaded function is named the exact same thing, but it takes different arguments. So with our overloaded constructor, with our rectangle example, it's going to take 2 doubles. So we define it the same way, but we include the doubles within the parameters. So rectangle, : rectangle, open parentheses, blah, 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 close parentheses. This one is going to take the width we pass in and assign it, and then assign the length that's passed in also. And then this is an example of the call statement. So notice how we add the parentheses for this one. So rectangle, we are making a new rectangle and we are passing in 10 for the width and 5 for the length. And then I'm going to crack open rectangle version 4 for you. For you. And just so you can see. So right here is our overloaded constructor. It's going to say, hey, what's up? And then the rest of it is the exact same. Within rectangle.h, if you'll notice, we have inline getters. And then within our driver.cpp, we input our 2 variables, width and length. We call the overloaded constructor, and then we output everything. So let me get this swapped over. Rectangle version 4, compile all, a.out. in feet, how wide is your house? We'll say 10. How long is my house? Let's say 20. So, what's up? So our overloaded function, our overloaded constructor is called the house is 10 feet wide and the house is 20 feet long, then 200 square feet of area. If you'll notice, we don't set it because it's already set with the overloaded constructor. Then we output everything. Ooh, yippee. So, constructors with default arguments. So, moving over to Sail version 2, if I can find it. So, crack these open. Yes. So we have our Sail class. We have an item cost and a tax rate for all of our items, or for all of our sales. How much money are we making? We have a default constructor, and we have a overloaded constructor. Actually going to add default to this. And then over for the overloaded one. So in our Sail, we have a default cost is equal to 7.5 and a double rate that is equal to 0.05. A couple getters and a couple setters. Get tax, we calculate the tax of the item. And then get total is going to return item cost plus get tax. So we have to enter the cost of the item. This creates a Sail object for this transaction. That we specify the item cost, but we use the default tax rate of 5%. So if you'll notice, we are only passing in item sale cost. Apparently I am lost. So, oh, no I'm not. I'm just a goober. So item sale is our object. So sale is the data type, item sale is the object. And we are passing in cost for the constructor. If you'll notice, we don't have a one parameter constructor. We have 2 and 0. So what this is going to do is it's going to say, hey, we are passed in a cost, but we don't know the rate. So let's use this number that's already here. So it's going to use 0.05 for our tax rate, and whatever number we enter for our cost. Then we output everything. So cd Sail version 2. That doesn't look good. So as I was saying earlier, standard, it's just a pain in the butt to type. Oh well. See how it was not standard. Standard. Wow, it works. First try. We run it, enter the cost of the item. I want to be funny. So it calls the overloaded function. So the one with the cost and the tax rate already set. We are changing the value of cost to 420. 5% of 420 is 21, and the total amount of sale is $441. So, that's cool. With classes, you can use the this implicit parameter. It mostly just improves readability, but it also helps the compiler distinguish between two variables. If you are I don't want to say a bad programmer, but if you're like me and you name your stuff the same things, I can be more specific. Your parameters and your variables the same name. So in this case, if double was item cost and if cost was item cost and rate was tax rate, you could distinguish between the two of them. Because what this says is, hey, use the current object's version of this for this variable. So down here, we have this item cost. So the compiler knows, hey, I should use the item cost that's found in this class. not maybe one that gets passed in. So, more practice, make a default constructor. Crazy. Super difficult. Next, we have destructors. Destructors are usually called in two areas. Whenever you dynamically allocate something and delete it, or whenever your program ends. Destructors don't have return types, they don't take arguments, and they can't be overloaded. It's the exact same name as the constructor, but it comes with a tilde in the front, or a squiggle, whatever you want to call it. So this rectangle has a destructor, and all it's going to do is say, hey, I'm destructing. So destructor is called when the program ends. It's also called in another situation if it's dynamically allocated and you go to delete that. A use case for that is if in your object you dynamically allocate something, you need to delete it and then delete the object. Or I guess it would be delete the object first so it gets deleted. Order operations, who needs them? So looking at rectangle 5. See, let's go ahead and skip down to the destructor. All this is saying is, I am in the destructor. Goodbye, cruel world. Then, can I see the driver, please? There he is. So, it's the exact same program. It's rectangle. We're taking input, creating the rectangle, outputting everything, and then ending the program. So let's go ahead and get moved over to rectangle version 5. Compile it. 10, 20, 200 square feet. Whenever we hit the return 0, the compiler is going to want to clean up everything it's worked with, and that's going to call the destructor. So I am in the destructor. Goodbye, cruel world. More class practice for you. Add a destructor function to your planets. You know, you want to blow up planets? Now you can. So operator overloading. We've talked about overloading functions. You can also do operator overloading. This is probably something I need to practice more. I don't practice it enough, but it really simplifies working with classes. So without it, I'm just going to go over here and do it. Add page. Without overloaded operators, what we have to do to, output data about it is cout. Let's say our book object is called A. We have to do A dot. I already messed up. Womp womp. Get num pages. And we do something with it. If we were to overload our classes, I have no clue what this is called, alligator signs, what we can do instead is just cout our book. So just A. So if we go back to our slides, we can see contact info version 1. Where did I hide that? Nowhere, apparently. So go ahead and crack this open. We have a contact info class that takes char pointers, so strings, char arrays, for the name and the phone. And then whenever we make a new contact, we take in the pointer. No, we take in the pointer to the number, the pointer to the name. We make new temp arrays. So temp array name, temp array phone. We allocate enough memory for the size of n and p, our name and our phone number arrays, plus 1, throw it in, copy it over, and then we set the new variables. So this name and this phone are equal to our temporary names. If you'll notice, these are pointers, so we are actually pointing to these strings that are created, instead of just name and phone having the values. Within our contact info, we delete what we made up here. Not contact. Within our destructor, sorry, we delete what we created. Then we have get name, get phone number, and finally our overloaded alligator signs. I'll be real, I have no clue how this works, but it works. So we say, hey, friend OStream, ampersand operator, and then we give it the operator we're overloading. So we say, with this output stream, OS, parameters. So one parameter is going to be an output stream, and the other one is going to be the contact info that we are printing. So we say, to the stream, we print the name and the phone number, and then we return the stream that we created. I have no clue what friend does. I will be looking that up. So looking at our driver, after all of this wonderful stuff, it's kind of simple. We are saying, hey, make a name and a phone number, make a new contact info with that name and phone number, and then print the stuff. So whenever we see out entry, that is actually calling our friend OStream ampersand operator alligators, or two less than signs. So this OStream OS is being passed in as C out. If we were to pass in a file, it would be passed a file. Then whenever we say, hey, what contact info do we print? That one. The one we're trying to print. So let's go over to contact info, compile all, and then run it. I have no clue why that's doing that. A.out. So two different ways to print it. You can either type it, so name is equal to entry.getName, phone number is equal to entry.getPhoneNumber, or you can overload your less than operator. So the capital one is the overloaded one, and it works. Crazy. So finally, we have namespaces and templates to finish off on. So namespaces, the way I always explain them is sort of dialect. If you think about a toboggan up north, it's a lot different than the toboggan down south. I believe toboggan northerner. So if you look at a toboggan up north, it's a sled. Look at, if I can spell, toboggan down south, it's a hat. So namespaces are dialects, or just sort of gives context. So if I say, hey, take a seat, you're probably assuming it's going to be the seat that's in front of you or the seat that's around me, and not the seat in the Capitol building of the country. If you say a table, talking to an accountant, they may think of an Excel spreadsheet. If you say table talking to a chef, they're going to think it's something you eat off of. So there's a solution to fix all of this mumbo jumbo, and that is namespaces. So with your class, you can say, hey, namespace auditorium, or namespace whatever context it may be. Then inside that namespace, you can define your class. And so if you remember earlier when I was having such bad trouble saying, hey, see out, it's actually part of the standard namespace. So whenever you put standard cout, it's going to say, hey, I know where to look for that. I'm going to go look in std. So with your classes, it's the same song and dance. You could build a class out of it. So if you were to rewrite the string class and say, hey, I want to use my custom string, you could say namespace mine class string close all of those, and then whenever you reference it, you can either use using namespace mine or mine colon string ... I will be real with you. I've never done these. Whenever I took this class 6 years ago, we did not touch them. I have not touched them in the 6 years I have not had this class. So, food for thought. There are a couple examples, namespace at top, namespace throughout code, and boss monster programs. We'll take a look at boss monster just to hammer home. Boss monster with namespace in 2 files. So that's not what I want. Let's look at the .h. We have a namespace monster. So within our namespace, we have a class boss monster, which has hit points, treasure symbol. That is not spelled right. Womp womp. Weight in pounds, height in inches. We have a boss monster. Is that a constructor? I think that's constructor. Fight hero monster wins, get hit points, get treasure symbol, get weight in pounds, get height in inches. Here's the constructor that's written. There's fight, all these getters and setters, and it's all within the namespace. If we look at our driver, we say, hey, from the monster namespace, grab the boss monster class, name it, and give it some stats. And I'm just going to go ahead and play the game. I'm a gamer. I don't need to read the instructions. Boss monster program, 2 files. What treasure do I have? We're going with thief. I've got 20 hit points. Do I want to fight it? Yeah, I want to fight it. We won, baby. We won. If rancor.fightheromonster wins, I'll dig into this code. I'll figure out if that was a fluke or not. I am pretty good at gaming. So, finally, we have templates. Man, we're at the hour mark already? Man, can this guy yap. So, templates are another one of the dry principle. Don't repeat yourself. So a function template is a function definition having a special type parameter, which basically means, hey, whatever you give me, I will use. If you give me an integer, I'll run this for an integer. If you give me a double, I'll run this for a double. This really prevents you from having to repeat yourself. So here we have 2 functions, one for integers, one for doubles. It does the exact same thing. We are finding we're just totaling the array, but because of size differences, we use 2 of them. What you can do instead is use a template. So at the beginning of your function, you want to put template, type name, t. It doesn't have to be t. T is sort of the standard, but call it whatever you want. Call it Steve, call it Jim, call it your favorite swear word. So within the actual code, whenever we reference, let me go back to these. So whenever we reference the data type, so in this case integers, in this case double, we are going to use t, or whatever you end up calling it. So t, or it returns type t, it takes a type t as an argument. We create a type T for total, sum it up, and return total. And we're going to go take a look at function templates.c++, if I can find it. That's the next one. Oh, phooey. There it is. So we have function templates.cpp. We have a getData function with a type name of llama. So void getData type llama, or an array of type llama. Down here we have getTotal type llama again. We have getLowest type llama. GetHighest type llama. And then we actually have our main. So looking over it, so we have a test scores and a game scores array. One is an integer, one is a double. So test is a double, game scores is an integer. And we're looking at the total, average, lowest, and highest for this. So let's back out to that. G++ function templates, and run it. Score for, it's going to make me do this. Okay, so if we sum 1, 2, 3, and 4 together, there are 10, the average is 2.5, the lowest is 1, and the highest is 4. How many times am I going to have to... 6, 7, 8, 9, 10. Oh my gosh, total 55, average of 5.5. I should actually run that again. Hold on. 100.1. 556, it's 69, 420, and 11. So if you'll notice, this works with both doubles and integers. Because whenever we look at this, we say, hey, we are passing in test scores. Test scores is a double. And so in these functions, it's going to replace llama with double and use double instead. Whenever we get down here, it's going to take game scores. Game scores is an integer, and it's going to replace all of these llamas with integers. So templates are the big thing you should take from this. You know, I'm already assuming that you know how to work with objects and classes and all that fun stuff, but functions are bread and butter, fantastic. You know, it's I want to say it's the one thing I can point at and be like, oh, look, I've seen these in the real world before. But it is. So class templates allow a class to have attributes that are template parameters as their data types. So already went over the example. Here we have booyah. So within our class, it's going to have two numbers of type booyah. And whenever we work with it, it's going to be of type booyah also. Whether booyah ends up being an integer, a float, a double, a short, whatever it may be. So you can have these class templates in separate files. A look at Plainbox example in Plainbox folder. We will go and find it. So plainbox.h, we have type item type. Doing some stuff with it apparently. The plainbox.h is grabbing plainbox.cpp. So this is where all of our functions are going to be. So we have item type, item type, item type. If you'll notice with our classes, we have to put a less than sign and the item type greater than sign. Or put them in alligators, whatever you want to think about it. So this says, hey, within our class, we are going to use this class declaration. Is it this line? Or this class type. So going back here, if we look at our main, we're saying, hey, I'm going to make a box of doubles and a box of strings. Apparently the box has health, but you get the idea. So with our number box, we'll always print a number, and then with our string box, we are going to print our string. So, two big things to keep in mind for this chapter. Templates are badass and fantastic to use, and whenever you use templates with classes, you have to tell it in your declaration what type it is. Either a double, a string, etc. Keep opening the wrong thing. So you can throw it in separate files if you want. Here's some class practice for you. Create a template class. I'm going insane. So if you want to do this, go for it. Make files. Manually compiling and linking a program. It gets painful. It gets really painful. So VS Code allows you to create a JSON file that will automate the process of compiling and running your program, and you can use a project management tool called Make. I'm not experienced with creating the JSON file. You may want to check Google and YouTube and all that for it, but it will probably help. It will most definitely help. The Make utility uses a makefile to recompile and link a program whenever changes are made to a source or header file. So, I didn't learn about this until my senior year, so it's kind of sick that it's here. And looking at a makefile recipe, so what it says is, hey, we have a target, and to make, our target, we need these things to make it. And it will check, hey, for target, to make target, I need P1, P2, and P3. And it will check whatever directory you're in. It says, does P1 exist? If it does, we check P2. If P2 doesn't exist, we need to come down here and run the P2 rule. So P1, P2, P3. So this matters whenever you're working with beefier C++ programs and you have to link things in, make object files. If you have to work with assembly, you often have to, you don't have to, but using a makefile make things easy. So let's say P1 is going to compile file 1. P2 is going to compile file 2. And P3 is going to compile file 3. So this is a very bare bones example just to show. Now going back to the real example, down here, I'm going to zoom in a bit actually, we have all. So the target all is going to make program 1, and program 1 needs quite a bit to run. It needs program1.o, videogame.o, videogame-library.o, text.o, and once it has all of these, it's going to do G++, all of the .o's, and make the .exe. To make program1.o, we need program1.cpp. So G++, I have no clue what that mine is. I think that's linking. So we're going to compile, and I believe, hello. So to make the targets, we need the prerequisites, and each prereq has a command to run. Do I have this? I hope I have this. I don't know if I do. Oh well. But if you want to make your life easy on these bigger programs, make a makefile. It's super helpful. So, I hope you survived the hour and 10 minutes of me talking. I need a drink. My throat is gone. Okay. Signing off. Have fun. See you in Chapter 3.